Hello everyone, and welcome to this webinar where we will be talking about applying deep learning to a manufacturing use case. I'm Thomas Carlson and I'm the enablement manager here at Peltarion. What we'll be doing today is to look at a deep learning use case within the predictive maintenance area, and we will present the background and the business case for it to then walk it through end to end, starting from data preparation, model building, to then evaluating and looking at the results. This is a demo that's going to be led by one of our data scientists and will be built up using that end-to-end workflow, but we do think that we will have time for some Q&A as well at the end of the session. And that data scientist who's going to take us through it is Mikael Huss, who's working here at Peltarion. He's well experienced within the machine learning and deep learning area and has worked both in industry and a number of years in the academic world as well. So there will be a lot of good insights that I think we can get from Mikael today once he shows us this use case. I should also mention that before we start, that this is the second webinar in a series of 2 different webinars. Some of you may have joined us last week when we had a webinar in collaboration with one of our partners, Futurize. That session was focused more on giving an introduction to the AI space and how it relates to different manufacturing companies. We also looked at some use cases and looked at some best practices. If you couldn't attend that one, I can recommend to check out the recording, which is available on our website. But let's focus on today's webinar. But before we jump right in, I just wanted to say a few practical words around the webinar itself. So we're using a tool called GoToWebinar, and as you may have noticed, we muted all the phone lines, and those will stay muted while we present. However, there is a questions and chat function in this tool that you should find on your right-hand side of the screen. Do feel free to post your questions. We should have time at the end, as said, to review some of those, and we'll also follow up after the webinar if we don't get time to look at all of them. I also want to highlight that this session is being recorded for those who couldn't attend. But with that said, I now like to hand it over to my colleague Mikael, who's going to take us through the predictive maintenance use case.
Thank you, Thomas. Let's see. Yes, so my name is Mikael Huss, as Thomas said, and I'm going to show you how to do an end-to-end use case with the Peltarion platform. Some of you may have seen the webinar from last week and will recognize some of the content that I will go through in the beginning, but it will be a bit more meat on the bones, so to speak, this time. So we will talk about a predictive maintenance use case, and what we mean by that in this context is techniques designed to help determine the condition of in-service equipment in order to estimate when maintenance should be performed. So instead of waiting until the equipment breaks or doing regular checkups, you do it in a more predictive way. PwC recently released a report where they talk about different levels of predictive maintenance maturity, from visual inspections via instrument inspections, real-time condition monitoring, to what they call level 4, which is characterized more by continuous remote inspection, statistical decision support, and data scientists being involved next to the reliability engineers that you usually have. And the particular use case we selected for today is solar panels. And the largest solar power plant in the world has 2.5 million solar cell modules, which is quite a number. The terminology here is that a module is made up of individual solar cells, and these modules are in turn making up arrays or panels. So the largest solar power plant has 2.5 million of these modules. And it goes without saying that even if you have nice monitoring equipment, you cannot really do this manually. You would like to have an automated way to do this if you want to be able to do predictive maintenance. So our use case for today is based on a data set collected by researchers in Bavaria, an institute there for applied energy research, and it's about electroluminescence imaging of solar cells, where current is injected into the solar cells, which will then emit light at a specific wavelength that can be imaged with a sensor. And this will make defective parts of the solar cells turn darker, get a darker color in the resulting image. But you can also see more subtle defects, such as the micro cracks that are shown here on the screen, or something called grid fingers. And these are things that you cannot necessarily see by eyesight. And these data were collected by the researchers that I mentioned, and they have also provided them for download online on this link here. So it's about 2,400 images, which is actually not a very big data set. The images are 300 by 300 pixels, and each image has been annotated by a human expert with a probability of it being defective. But this probability is only annotated in 4 different levels. So if the human expert thinks that it's not defective and is pretty sure, then the number will be 0. If they think it is defective and they are pretty sure, it will be 1. If they think it's not defective but are not sure, it will be 0.3333. And if they think it's defective but are not sure, it will be 0.6666, so 2/3. And they have also put up a nice manuscript about this online, which is also linked here. And what their model that they arrive at in the end does is that for each image of a single solar cells of where you have many here, their model will assign a probability between 0 and 100 or 0 and 1. So while they only annotate it in 4 different levels, their model actually predicts a continuous value in the whole range. So you could either see this as a regression problem where you predict a continuous value, or as a classification problem where you predict which class the solar cell is, defective or non-defective. All right, so what did they do in this paper? They used a type of convolutional neural network, which is a very common type of neural network nowadays for image processing. And we will not go into too much detail because there is not enough time, but just to explain very simply, in convolutional neural networks, an image is processed in several stages, in several layers, where usually the first layer tends to pick up simple features in the image, such as bars oriented in different directions, for example. And then it gets sent to the next layer, which can combine simple features from the previous layer and thus detect things like corners or circles or things like that. And in the next layer, it can detect even more complex or already quite complex patterns and things like that almost look like maybe buildings or faces. And this is done by using trainable filters. So you don't predefine what these things are looking for, but the convolutional neural network is able to learn the filters that detect these different features. So again, speaking in a very simplified way, when the neural network sees an image, it processes it through consecutive layers of convolutions and pooling operations and some other operations. These are also called layers, convolutional pooling layers. And as I mentioned, the convolutional layers are picking up and combining different image features, and the pooling layers are combining information from small parts of the image into well, less high resolution images. The images get progressively coarser, but they sort of contain more information about what features there were in the image. So at the end of this network, you have some very coarse pixelated image, but which contains hopefully enough information to classify what object the image contains, in this case a car. This is just to give some background on what we will see in the platform. And another thing I wanted to mention was that the authors of this paper used something called transfer learning with their convolutional neural networks. That is when you have pre-trained a model on a different data set than the one you have in order to help it along a little bit on the way. This is especially useful when you have a small data set like we have here. So in this case, they used a pre-trained model that had been trained on recognizing images from ImageNet, which is a very big collection of millions of images from the web, each of which has been annotated with one of 1,000 classes, like dogs and cats and cars and buildings and things like that. And the network has to learn to recognize them. So the idea is that by training on a very large number of natural images, the network will learn to extract useful features for classifying any type of image, basically. And then what you can do is you can take that model and fine-tune it on your own data from your target domain, like the solar cells in our case. And the pre-training will help it have a good set of parameter settings that you can then fine-tune. So we will see how you could do that as well in the Peltarion platform. So what I will show is data import, model building with 3 different types of convolutional neural networks. And then we will look at how to evaluate the models. And finally, we will look at how to deploy the model, and if we have time, how you can inspect your predictions outside of the platform in a Jupyter notebook. So that's it for my intro, and let's jump into the Peltarion platform. Okay, so let's go back one step. So the opening view of the platform looks like this, and now I'm just going to click into a project that I made for this session called Predictive Maintenance Webinar. And we will now enter the dataset page where we can import data. You can import data in several different ways. When it's an image classification problem like this, you can either choose to upload a zip file that you have locally on your machine, or you can import a file that you have placed in a Google storage bucket, which I will try to do now. I have actually got 2 versions, two versions of this data set because it takes a while to train these models. So I have one data set with the original size images and one with resized images. But let's try to import the full size images. So now you see that they are being ingested into the platform. We have to wait a couple of seconds, and then we should get a preview of what this data set looks like. Still processing. in case we experience bandwidth issues, I should have some pre-loaded versions of the data as well. Okay, so let's call this demo full size, and now we get a view where we can pre-process our data and define some different things that we need to define. So in the first column here, we see some thumbnails of the images, so you can make out a little bit what they look like. Here you can apply different transformations to your data if you want to. You can let them stay as they are, or you can do min-max normalization, which if you don't have the full range of pixel values in an image between 0 and 255, you can take care of that by using min-max normalization. You can also do standardization, which I think we will do here, which is subtracting the mean of all the images from each image and dividing by the standard deviation, so that you get on average a mean of 0 and standard deviation of 1. The next column is a defect probability, so it's the one I mentioned with 4 different values that have been assigned by human experts. The platform sees that this is a floating point number and wants to standardize it, but we will want to keep them as they are because they are labels from the human experts. The next column is something that I didn't mention before, but these solar cells come in 2 different variants in this data set, monocrystalline and polycrystalline solar cells. So there's information about that as well, but we will not use that information today. The next column is something that I defined in advance, or we have a pre-processing script that will create these things. If you want to check that out, I can show that later. But this is about defining which samples, which images should be in the training set and which ones should be in the validation set. The training set is the set of images that is used to fit the deep learning model. And the validation images are the images that are not used to fit the model, but are only used for evaluating the accuracy of the model. And it's important that we know which images are in which data set, especially if we want to evaluate the model outside the platform, like we will do today. And finally, we have a column which is called binary class, which is a way to convert these 4 numbers that the experts have assigned into 2 different classes. So here we only care about whether the solar cell is broken or not. So broken is 1 and not broken is 0. So everything that is above 0.5 is considered to be 1, and everything below 0.5 is considered 0. And we will use that as a classification target. And when you want to use a classification target, you should select the one-hot encoding preprocessing method. All right, so now we come to 2 other things which are in the side panel here. The training and validation subsets, which I already touched upon. And the platform by default makes an 80 by 20% random split, but I don't want to use that in this case because I want to use my predefined split that I had done in advance. So we select a condition. Feature subset should be equal to V for the image to be in the validation set. And for the training set, it should be equal to T. We talked about normalization as well, for instance, the standardization. So the statistics for doing the standardization, the mean value and the standard deviation, those should be based on the images in the training data set, and then they will be applied to the validation images as well. The last thing we need to do is to define the feature sets, which are the inputs and outputs, if you will. So we want to have the image as an input, of course, because that's what we want to classify. But then we want to have outputs, and we can make two separate ones. One which is a class, 0 or 1, and one which is a probability, where we can try to predict a continuous value. And now I think we should be all set to save this version of the data. So I click Save Version. And this will lock this version of the data set so that you can't modify it anymore. This is important because it's good to know exactly what version of the data you used. If you want to change something, you can always duplicate this version of the data or some other version of the data and make the changes that you want to make. In this case, I don't think there are any things that I want to do. So now we have this green check mark here, which means that this version of the data is ready. So we can go to the modeling view. You can see that there are 4 different views here. So we'll go through them one by one. Now we can go to the modeling view. And here we can make what we call experiments, which are essentially deep learning models. And we click New Experiment. And for this first one, I would like to show the simplest way, I think, to get a pretty good classifier, where you have to do the least in order to get a good model. And that's by using a predefined state-of-the-art model called a DenseNet. And here on the right-hand side, we have ways to build up your models. We have something called blocks, which are the basic building blocks, like the convolutions and poolings that we saw. But there is also something called snippets, which are predefined models. These are all based on published papers and are models that many people are using. And for each of them, we try to give some information on what they are good for and when you might want to use them. So let's take this DenseNet 121 as our first model. Now you see this incredibly high stack here with many, let's zoom in so you can see this is a very, very deep neural network. So if you would zoom in here, you would see all of these layers, convolutions and activations and max poolings and so on that we discussed. And this is a very deep network, 121 layers, but it has already been built for us. So we just need to fix the missing information that we get warnings about here. So of course we need to have an input, and for that we select the image that we defined as a feature set on the dataset page. We need a target, and let's select the class as the target. And now we have another error, which kind of makes sense when you think about it. It says the target block expected a shape of 2. That's because we have 2 classes, not 1000, which is the default. And it's the default because ImageNet has 1000 classes, and but we only have 2. So now we have yet one more error, which is exceeded the total allowed memory of 5 GB. So this neural network model is very big, as I've said repeatedly, and that in combination with the size of the data, the size of the batch of data that the model gets each time makes it too big, namely 10.71 GB. And we are running on a graphical processing unit, a GPU in the cloud, and we have set a limit to 5 GB. So you have to get your model size down to below 5 gigabytes to be able to run this. And the easiest way is to decrease the batch size to, for example, 12. So the network will see 12 images in each batch. And then we need to choose the number of epochs, and an epoch is it means that the neural network sees each example in the training set once. So if we put 10 here, it will go through all of the examples 10 times. And this model, because of its size and because we are using full-size images, will take a very long time to train. So we will start it, but I don't think we will look at this model anymore because it takes several hours to reach a good performance. But still, it's the easiest way to get a good model quickly. So let's then look at transfer learning. We mentioned the transfer learning approach that the authors used in the paper. And for that, I have uploaded a pre-trained model into the platform. So this is something that is possible, but is not yet exposed in the graphical user interface of the platform. It will be introduced as an option fairly soon, within the next month. But for now, I have uploaded this VGG19 model pre-trained on ImageNet, which is the same as in the paper. And let's also put the, let's see. All right. Yeah, I should also say that we should replicate exactly what they did in the paper for this. So what they did was they kept only the convolutional part, only the image processing part, if you will, of the VGG19 model, and they took everything else out and replaced it. Let's see what's happening now. Replaced it with their own architecture. I'm not getting any reaction here. Let's see if there is some. Oh yeah, sorry. Sorry about that. I should have duplicated this model first, so that I don't modify the originally uploaded model. So now we should be able to, to put the features here, the image and the final part of the model should be cut out and replaced by the operations that they used in the paper, which was 2D global average pooling and then some dense layers connected to the target. And the target for them in the paper was not a class, but a probability. So let's use that, and we use the mean squared error as the loss function for that. And the sizes of these dense layers should be like this according to the paper, and the last one needs to be 1 because we only have one output, namely the probability. And the activation function should be a sigmoid because that is a function that transforms the output into a continuous scale between 0 and 1, which is what we want in this case. And again, our model is too big, 28 gigabytes, so we can dial it down to 32, for example, and then we can train. Right, I forgot one other part of what they did, so let's do that as well. Another thing that they did in that paper was image augmentation. This is a way that you can create more training data for yourself by constructing synthetic versions, a bit tweaked versions of the images that you have. This is good to get more training data, as I said, and to make the model a bit more robust to things like rotation and changes in lighting and so on. For these solar panel images, as you may have seen, they aren't ever really rotated, so it doesn't make sense to use the rotation augmentation, but we could allow up to 0.2, up to 20% horizontal or vertical shift up or down, right or left. We could allow it to zoom a little bit into the images, and we could allow it to do vertical flips. If you want to learn more about image augmentation, there is a link to the Knowledge Center in the platform where you can read all about image augmentation. But yeah, that's something that they used. And another thing that they also mention in the paper is that after changing that last part of the pre-trained model, they actually froze the weights of the convolutional part in order to keep the feature extraction from the images constant, so that the network doesn't forget how to extract these features. That can be done by marking those blocks and selecting trainable equals no. So let's do that as well, just for completeness sake. I think I need to go in a little bit here. So those are not trainable, and those are not trainable, not trainable, and not trainable. And then we can run that one as well. The final thing I wanted to show was how to build your own convolutional neural network from scratch, if you kind of know how these things work and you have a sense of how to do it. So for that, we should use the resized images, because otherwise we will not have time to look at the results. Resized. So now I will have to do all of these things that I showed you before very quickly. But I hope that will not take too much time. It's the same division into training set and validation set. And then we also need to define the inputs and outputs again. So these images are just 64 by 64. And we can save this, and it's already finished. So if you want to build your own simple CNN, which can actually be quite effective, I usually do it like this. I take a stereotypical block of convolution, batch normalization, and max pooling, and repeat it a couple of times. We've talked about the convolution and pooling blocks. The batch normalization is a block that usually helps the model to train faster, gives a more smooth training course of training, and is often good against overfitting. So you can see here the dimensions of the images, how they get smaller by convolution and pooling, and at the end we have this coarse image of 6 by 6 pixels and 32 filters. And now we need to flatten it out somehow to just a list of numbers that we can send to the dense layers that will combine these features in different fruitful ways to be able to predict the class. Should put the class as the target, and then we use categorical cross entropy as the loss function, because that's the loss function that goes together with classification, and we have softmax as the activation here at the last layer. Can turn this down a little bit, and now the model is much smaller, so we can set the batch size to something big like 320, and we can let it run for 100 epochs. You can also play around with the optimizer and so on, but the default one, Adam, is usually quite good. So let's start with that and train this model, and then we can move into the evaluation view and see how our various models are doing. Right, so if we now go to the evaluation view, we can look at the models that we have started and see that the first one, the DenseNet, has only trained for 2 epochs because it's slow, but we can nevertheless look at what the view looks like. So up here are some training curves, which I will come back to soon, but maybe the most interesting one is the confusion matrix down here, where you see the predicted class on the x-axis and the actual class on the y-axis. So for example, we have 56 images that showed defective solar cells that were also predicted to be defective. But on the other hand, we have 79 defective solar cells which are predicted to be not defective by the DenseNet. So we are only picking up 41.5% of the defective ones because the DenseNet hasn't had time to train properly yet. On the other hand, we are very good at recognizing non-defective solar cells, and now the numbers were updated because it evaluated a new epoch. So this is the confusion matrix. When we are doing regression and trying to model a continuous value instead of a class, yeah, this is not a good illustration. Let's go to this one. Then the plot looks different. It's not a confusion matrix, but a scatter plot where the actuals are on the x-axis and the predictions are on the y-axis. And as you remember, there are only 4 possible values of the ground truth, but the predictions can span over the whole range. So that's what is shown here. Maybe easier is to look at this histogram of errors, which shows the actual minus predicted, where this also hasn't had time to train much yet, but you would in general want to have a spike in the middle at zero error, and not so much to the right and left. So if we look at a model that I trained before this seminar that is pretty good, then it looks like that. So that's a nice error profile. And then to come back to the training curves, if we look at the simple CNN that I made just now, we can look at the curves for the training images, which is this thin line, and the validation images, which is the thicker line. And typically the training error will be lower because the training images are the images that are being used to fit the model. And the validation error is typically higher, but in this case it's even worse than that, because after a while the validation error started to diverge. So now the model is not generalizing well at all. It has a low training error but a very high validation error, and this is what we call overfitting. So the simple CNN was not clever enough to avoid overfitting. If you look at a model that I trained before that is quite good at classification, you see a much nicer consistency between the training set and the validation set. They have almost the same error, and this model reaches 86% accuracy. But unfortunately, we don't have time now to reach that kind of results. Right. Yeah, I can mention also that apart from accuracy here in the right-hand panel, you have other measures such as the area under curve for a rock curve, if you're familiar with those, and we have an average precision and average recall for each class. Whereas if we are doing regression, we have root mean squared error, mean absolute error, R squared, and other measures. Mean absolute percentage here is absurdly large because we have some labels that are 0 in this case, and that will lead to dividing by very small numbers, so that is not meaningful in this context. So let's say you have trained a model that you are happy with. Now you can go to the deployment view, and here you can select a new deployment. And if we had been happy with this very overfitted simple CNN, we could have we can select that, and then you choose which checkpoint you want, the one that was best according to validation error, or the last one. So usually it makes sense to take the epoch where it was the best, and then you can give it a name and create it, and you will get a page which shows credentials, an API endpoint that you can call, and a token used to authenticate against that endpoint, and some information about what the inputs and outputs are called and what their dimensions are. If you just want to try it out and classify, for instance, one image from the command line, you can copy this code here and just insert the path to your file, and it will return a prediction in JSON format. But of course, you get the most value out of this by perhaps building an app around the prediction API, or as I will do now, look at some predictions in a Jupyter notebook by using Python. So Peltarion has released a software library in Python called Sidekick, which is a way to get data into the platform, for instance, making these zip files that we are uploading, and to get predictions out in a nice way. There is a lot of documentation here about how you do that, how you get the predictions out. So basically, you have to use all of the information that you see here on the deployment page, and you create a Sidekick deployment object with the endpoint URL, the token, and the other information about the inputs and outputs. And when you have done that, you can call the API. So here I have just selected some random images from the training and validation datasets and visualize them, and then we show the ground truth and the prediction. So for this image, it was annotated as defective, and the network, the model, which is one of these models that I showed before, that I had trained in advance, shows 88.6% probability of it being broken. Then we have another one where the ground truth is a third and the prediction is 0.78, so it's not agreeing with the human annotator there. Another one which is broken where the prediction is over 90%, so that's good. Another broken where the prediction is 0.76, so that's good. And a one that's whole where the prediction is very low, so that's good. So that looks okay, and we can go on to evaluate on the whole validation set to look a bit closer. We already know from the platform that the overall accuracy was 86%, but we can get all the predictions out in a data frame and compare those manually with the annotated probability and the binary version of the probability. So again, the accuracy is 86%. We can look at other performance metrics And in particular, we can draw a ROC curve if we want to maybe examine not using 0.5 as a threshold, but rather try to vary the threshold for what is considered a positive or negative prediction. And by doing that, we will trace out a curve that shows the trade-off between false positives and true positives as a function of the threshold. We can look at the distribution of predictions per class. So the orange bars here are images that are actually broken, and they show the distribution of the predictions of the model on those. And the blue ones are the ones that were actually whole, and the distribution of the prediction that the model made for those. Of course, we can also do this by the original label, which had four different possible values. And here we can, for instance, see that the ones with defect probability 2/3 are very difficult for the model to get correctly. It sort of guesses all over the range, but there are not so many of those. We can also look at the most misclassified samples. So for example, here is one image that is annotated as defective, but the model only assigns a 7% probability of it being defective. And this could be interesting if you want to understand what kind of thing the model is not good at, and maybe try to increase data of that kind, this kind of images. Here is another example of that. So this can be a way to find out what kind of data you want to collect. And conversely, you can look at the ones that were not defective, but that the model claimed should be defective, and you can try to figure out why it thinks that they are defective. If we look at this image, for example, you could, I think we have a couple of more minutes that I can use on this. You could use a kind of technique to see what the model is looking at in that image. So for that, you need to do another thing that you can do in the platform, namely to download the model in H5 format. If you go to the modeling page and click here, you see that there is a download link, and that will download the model in H5 format. So you can do that, and then you can load this image that the model was claiming should be defective, even though it's not, and use one of many available methods to visualize the important pixels in the input, which pixels the model is sort of focusing on to say that this is broken. And in this case, it's highlighting this bar here, and that's what makes it think that this could be defective. So I think that will be the end of my tour of the platform, and we might have some questions.
Yes, perfect. Thank you very much. That's a comprehensive end-to-end demo. So as we mentioned in the beginning, we have about 10 minutes for questions. So you have a questions panel on the right-hand side of the screen if you would like to type your questions in. And I know that Mikael is going to do his very best to help answer those. And feel free to both ask about the model in particular, of course, but also if there are some more generic questions around the Peltarion platform or the project itself. And as it happens, we have a couple of questions that came in as you were presenting. So I think we'll kick off with those and see. So one question is quite broad, so I'll read it out the way it's been typed here so that we can see. Is the Peltarion platform able to create a model that would automatically gather relevant data set out of a big amount of encrypted data? In other words, creating the data set to be imported in another model. How would the tool in that case gather the right data to then process these relevant data with another model? I know that's a rather big question, perhaps, but
yeah, is it possible to get more detail on what this encrypted data means? The question is if the platform is able to create a model that would automatically gather relevant data sets out of a big amount of encrypted data. I'm afraid I would have to have a bit more detail on what these data look like and what form they are in.
Mm-hmm.
In general, the way you work with the platform now, you would typically need to collect your data yourself, if that is the question.
Mm-hmm.
We don't, for instance, have support right now for going out and collecting data from the web, collecting images or something like that.
So what we support with, obviously with Sidekick as well, is like getting the data into a format that can then be analyzed.
Definitely the Sidekick library will help you put together your data if you have collected your images, for example.
Yes, and there's a follow-up here from Maud, who's asking the question is, so it's about data from 3D printing machine systems as an example. So obviously collected by the 3D printers, I guess, sensors perhaps.
So in general, if you have data that is, for instance, images or sound or video or things like this, it will often be interesting to consider deep learning for building models out of those. Not only classification, but also, for instance, segmentation, to be able to locate precisely something in an image and so on. I'm sure there are many possible use cases for 3D printing machines, but maybe we would need to have a separate discussion about exactly what the structure of this data is.
Yes, and then to that point, actually, we're more than happy to follow up after these calls with some more, one-to-one advice in terms of, the particular scenario. But hopefully that gives a good overview, guidance on what the platform can do and not. If I move to another question that actually came in, and this was actually one that we got in last week's webinar, but unfortunately, because we had so many questions, couldn't address at the time, but it's also around the capabilities of the Peltarion platform, so I thought we could look at it now. And it's how the person asking the question is saying that they're working with processes and thinking about how to optimize plant operations with machine learning, and if there's solutions that Peltarion can support there, and specifically in terms of analyzing time series, if that's a support that the platform has today.
You can do time series analysis, although we don't have an explicit user interface for it, but the components to do various types of time series analysis are there, like, for instance, convolutions and other ways that we can discuss at a separate time. Mm-hmm. So again, I have myself done time series analysis, but it takes a little bit of data preparation in advance again, and then you can import them into the platform and use these blocks to build a model. And among other things, we have worked with manufacturing plant production line optimization, although maybe not exactly in the same way as implied by this question, but we combined tabular data from sensors and images and other sources to build combined models in the platform for that project.
Perfect, thank you. There's some more questions coming in. So another person is asking, is it possible to derive Python code for the model from the platform?
It's not something that is supported at the moment, at least. It's yeah, a possible extension, but it's not a functionality right now, and we will see. Yeah.
Yes, that's a good answer. Another question is around the so when you were building your models, you were obviously scrolling, especially with these bigger, many layers. I think this user was actually following alongside and saying that they're having some issues with scrolling in the modeling canvas, and whether there's a known issue with Chrome as a browser. I don't believe.
As far as I know, Chrome is the one where it works best.
Yes, I was about to say the same. So,
but yeah, I guess it depends on what kind of problem it was. You can scroll with the Option key on a Mac, for instance, and then there are some ways to navigate more quickly, for instance, by clicking on those arrows, like I did, to jump back and forth between input and target.
Yes, and what I would recommend here is maybe in the right-hand corner, we have a link to our support, or actually in the top right-hand corner, there's a link to our support team that can actually help with that, and we would be very grateful if you wanted to just take a minute and submit that question and give us some information, and then our colleagues in the support team will be happy to help with these type of issues, and if there is something that's going on, and they can check on the specific scenario in that case.
Yes, but please report all issues. It's good.
Yes, we are thankful for that, of course. As with all tech solutions, there's always improvements that can be made, but no known issues is the summary answer. So those were kind of the questions that came in so far. So I'm just gonna, we have a few more minutes, so if anyone has any additional points, then feel free to type it in. While we wait for that, perhaps we can go to our presentation slide, and I'm just going to mention a few words around how you could continue engaging with us after this webinar. In particular, if you found the demo that Mikael did interesting and you would like to try this yourselves in your own environment, so to speak, then there are on the Peltarion website, we have a number of ways of getting in touch with us and engaging with our team. We're more than happy to follow up one-on-one with you after this webinar, in particular to answer your questions. I also wanted to highlight that there is Peltarion Jumpstart service, and what this is together with our colleagues in our tech team and the colleagues of Mikael, our data scientist, we can work together on a 6 weeks proof of concept project where we actually come in and analyze together with you your business scenario and present a solution on how deep learning could be applied in your environment simply. And there's some more information available on this particular service on our website. We should also mention that while the example that we presented today is not available as a tutorial, we have some other examples where we show the end-to-end workflow and where you can test the platform in terms of going through a tutorial and seeing how you build different models the way that Mikael showed today. So with that said, I'm seeing that we do not seem to be seeing any other questions, so we won't, knowing that we're also quickly approaching the top of the hour, I wanted to throw in one final piece of information here. So obviously what we've done today and last week was 2 webinars focused on the manufacturing industry. Coming up, we have a similar set of webinars that will hone in on healthcare and look at trends in the healthcare industry and also how deep learning can be applied in that context. So I just wanted to say that those dates are announced on our website. We will follow a similar format where May the 2nd is going to be a high-level review of the trends, as said, and then May 9th we will look at building a deep learning model the way that Mikael did today, but for a healthcare-related use case. So hopefully that might be relevant also for you who are listening today to tune in and check that out. And with that said, I think we want to, just as a final note, thank you for attending this webinar today. And we hope, as said, to see you online in one of our future sessions. So thank you very much for dialing in.